Okay, let's take a look at a couple extra examples here. Example 1b, same idea, same process of simplifying some radical expressions. And I guess I really should have given myself some extra room here. So I will rewrite my problems on the side here as we go through. But if you wanted to try some of these problems on your own, here are the problems that I'm going to do. So example 1b, let's start off simplifying the square root of 32x to the 4th y to the 6th. I can't square root 32 nicely. So let's kind of try to think back to some of those strategies we've used to simplify our square roots. 32, you can think of what's the biggest perfect square that goes into 32, and 32 is 16 times 2. We can square root the 16 and bring the 4 out front, and we'll have a 2 underneath my radical somewhere. So I'm just going to kind of leave myself some extra space here, put my 2 underneath. Now the square root of x to the 4th is x squared. The square root of y to the 6th would be y to the 3rd. Okay. I guess kind of like the easy trick for figuring out what these powers out front would be. Think of this as your second root. Your square root is really a second root. 4 divided by 2 is 2. 6 divided by 2 is 3. Okay. And you can kind of use that with remainders too if necessary. So I'll keep showing you guys that trick. But since I had an even root and an even power underneath, even root, even power underneath, my x squared and y cubed all needs to be an absolute value. But x squared is always going to be positive. So my final answer would really be 4x squared times the absolute value of y cubed times the square root of 2. And that's my final answer. So again, I don't need the absolute value around x squared because x squared is always positive. But y cubed needs to be absolute value because I have an even root, even power underneath, odd power at the end. In my next situation, the cube root of 27x to the 8th, y to the 10th. The cube root of 27 we can do easily, that's 3. The cube root of x to the 8th is a little bit tricky because x to the 8th is x to the 6th times x squared. And we can cube root the x to the 6th. So kind of using my different colors here, the cube root of x to the 6th would be x squared coming out. And I'd have an x squared underneath. X squared underneath. Keep in mind that this is really a cube root, so make sure that cube root gets in there as well. So I'd have cube root of x squared still over here. And then I have the cube root of y to the 10th. Well, y to the 10th is y to the 9th times y. The cube root of y to the 9th is y to the 3rd. And I still have this y that's underneath. And I don't need any absolute value because I have an odd root here. So final answer is 3x squared y cubed times the cube root of x squared y. Sounds kind of complicated. Last situation here, if I have the square root of x to the 6th, y to the 8th. Square root of x to the 6th, y to the 8th. My square root of x to the 6th is x cubed. My square root of y to the 8th is y to the 4th. And if I just jump to what my final answer would be, I'm going to end up needing the absolute value around the x cubed, not around to the y to the 4th. The y to the 4th doesn't need the absolute value because y to the 4th is always going to be positive because I have an even power here. But I need my absolute value around my x cubed because I have an even root and even power underneath. As I mentioned with that whole kind of dividing trick, it still works even if we have like a remainder here. In this middle problem that we did, we can't just do 8 divided by 3, but 3 goes into 8 2 times with 2 left over. Same thing here. We can't do 10 divided by 3, but 3 goes into 10 3 times with 1 left over. So you can still kind of use that shortcut if it's easier.